Today we're going to present a tutorial about learning augmented mechanism design. So my name is Eric Balkanski. I am an assistant professor at Columbia University in the Department of Industrial Engineering and Operations Research. And today I'll be presenting this tutorial with Vasilis Gkatzelis, who is an associate professor at Drexel University in the computer science department. Yeah, so this tutorial is going to be about this new area in mechanism design called Learning-Augmented Mechanism Design. So there's been the first few papers in that area this year, and we hope to convey to you that there is a lot of opportunity for a lot more exciting work in this area. And so I hope we also hope to make this tutorial as interactive as possible. So please don't hesitate to ask questions. So I think the best way for that is just to post them in the chat. When I'm speaking, Vasilis will monitor the chat, and when Vasilis is presenting, I will monitor the chat. Yeah, so good. Let's get started. So to motivate this area, I'd like to start by discussing worst-case analysis, which is the standard evaluation metric that we use in algorithm and mechanism design. So on the positive side, worst-case analysis gives us some strong robustness guarantees that can apply broadly to any instance. However, a main drawback is that it can also be unnecessarily pessimistic. So it often leads, for many problems, to some very strong impossibility results that don't necessarily reflect the obstacles that can arise in practice. And this is because the performance of algorithms and mechanisms are often significantly better in practice than the worst-case guarantees that we have for these problems. And so this has motivated a lot of work on alternate evaluation metrics that go beyond worst-case analysis. So one example, so a lot of these different approaches make some assumptions about the input to aim to go to overcome worst case impossibility results. So for example, there's been some work that make some some assumption about the structure of the instance at hand, or also some other lines of work that assume that the instance that we're analyzing is at least partially random and drawn from some distribution. So in this tutorial, we're going to talk about a different approach that uses ML predictions. So this alternate approach in the context of algorithm design is called Learning-Augmented Algorithm Design, or algorithms predictions. So in this approach, we don't make any assumptions about the input, unlike, for example, average case analysis. But instead, we're going to assume that we have access to some ML prediction about the instance at hand that we can use to try to obtain improved guarantees compared to worst-case analysis. Okay. So the motivation to have access to ML predictions is to assume that we have trained there's some ML model that has been trained over historical data about similar instances, and that given the features of a new instance, we can get a prediction about this instance. And so such an approach is especially relevant in settings where the main challenge is to overcome information limitations. So where some ML prediction about this missing information could play an important role. Okay, so what are we hoping to achieve in learning-augmented algorithm? So an ideal algorithm in this framework would achieve the following two things. First, we would like an algorithm that achieves an optimal performance guarantee when the prediction is accurate. So we want it to do extremely well when we're given a correct prediction about the instance at hand. But sometimes ML predictions can be inaccurate. And what we would do is that even if the prediction can be completely wrong, we would still want to maintain the worst case guarantees that are achievable for the version of the problem that we're considering where we don't have predictions. Okay, so these are the two things that we would like to achieve. And these two different objectives are formalized by the notions of consistency and robustness. Okay, so consistency and robustness are the two main performance measures that are used in algorithm with predictions. For consistency, it's defined as the worst case performance when the prediction is accurate. So more formally, we say that an algorithm is alpha consistent if the performance of an algorithm on any instance, when given a correct prediction about this instance, is at most an alpha factor away from the optimal value that is achievable for this instance. Okay. And now the second performance measure is robustness. So this is okay. There's a question in the chat about not hearing or seeing anything. I just want to make sure that other people can hear me. Okay, good. Thank you. That would have been bad. So the robustness is the worst case performance overall, regardless about the prediction, even if the prediction is completely wrong. So we say that an algorithm is beta robust if the solution found by this algorithm on any instance, given any prediction about this instance, is at most a beta fraction away from the optimal value that is achievable on this instance. So here, importantly, the main difference, right, is that for consistency, we assume that we're given a correct prediction about a worst case instance, whereas for robustness, the prediction can be arbitrarily wrong. Okay. So these two different performance measures are going to be very important for this tutorial. So let me discuss them a bit into more detail. So first, what are some trivial bounds that we can achieve in terms of consistency and robustness? So if you consider the version of a problem where there's no prediction, and if we have an algorithm that achieves a beta approximation guarantee for the version of this problem without prediction, then what we can do is that we can just completely ignore the prediction, just run this algorithm without prediction, and that would trivially achieve, it would be an algorithm that is beta consistent and beta robust. Now, on the opposite side, what you can do is, given a prediction, you can just assume that this prediction is correct and try to optimize for the consistency, assuming that this prediction is correct, trying to get the best consistency as possible. But now, as we will see later, if we just assume that the prediction is correct and optimize assuming that this prediction is correct, this can lead to some arbitrarily poor robustness guarantees. So here what we see is that there is this trade-off or this tension between these two different measures of consistency and robustness. And the main challenge of this framework with prediction is to try to achieve simultaneously good consistency and robustness with an algorithm. We want to find the optimal trade-off between these two different performance measures. Okay. So now, if you think about consistency and robustness, they're a bit at like the two opposite ends of a spectrum when you think about the prediction. Consistency is what you achieve when the prediction is perfectly correct, and robustness is the performance that you achieve when it can be arbitrarily wrong. Now, of course, in practice, what you might want to have is that you also would like to have good performance guarantee, even if the prediction is maybe a little bit wrong. So more generally, what we would like is to have some guarantees as a function of the prediction error that would kind of like smoothly degrade from the consistency bound to the robustness bound. So more generally, we're going to want to have this kind of like performance that smoothly interpolates from consistency to robustness. Okay, so this is what these are the evaluation metrics that we're going to use, that we use in algorithm with predictions. And so now let me discuss one area where this framework has been very well studied and has had a lot of success to overcome worst case guarantees. So this area is in online algorithms. So there's been a lot of work on algorithm predictions. And in online algorithm, a main challenge is the information limitation about the future. So there's a lot of uncertainty about the future. And in such problems, it's often reasonable to assume that we can have at least some kind of prediction about what will happen in the future. And so this framework has been studied for many different online versions of different problems, such as paging, scheduling, secretary problems, set cover, knapsack, facility location, national social welfare maximization, several graph problems. And here I'm just listing a few. There's really been a ton of work in online algorithm prediction that have revisited all of the fundamental online algorithm problems. And so in this tutorial, what we're going to discuss is the potential for this framework with prediction to also have a big influence on another domain. And this other domain is mechanism design. So in mechanism design, we also face a main challenge that is due to information limitations. And this is due to the presence of strategic agents. Okay, so now let me go over the outline for the tutorial. So first, we're going to go over online algorithm with predictions, and in particular the classical and simple ski rental problem. So here the main idea is that we kind of want to illustrate what can be achieved using predictions in this framework, in the field of online algorithm, which has been very well studied in this framework. And so we want to kind of like understand, okay, what is the natural notion of prediction? What can we do with the prediction? What can we hope to achieve? And then hopefully that then set the tone for what we also would like to achieve then for mechanism design. So see kind of like, can we obtain similar benefits in mechanism design with predictions than the benefits that this framework of prediction has brought to the field of online algorithm. So then for mechanism design with predictions, we will consider both problems in a centralized setting and in a decentralized setting. In the centralized setting, we're going for concreteness, we're going to mostly focus on the problem of strategic facility location, but we will also briefly discuss strategic scheduling and auction loss predictions. And then in the decentralized setting, we will mostly focus on improved price of anarchy bounds with predictions. Okay. So now in terms of like the structure of the tutorial, of the beginning of the tutorial, you can think about the tutorial as being divided into 4 different quarters, with the main break between the second and the third quarter. I'm presenting this first quarter that will end after we go over the ski rental problem with predictions. Then Vasilis will take over and give some background on mechanism with predictions, and we'll start covering strategic facility location with predictions. So as you will see, for strategic facility location, we're going to consider both the one-dimensional version of the problem, the two-dimensional version of the problem. Vasilis will then end the second quarter at the end of the one-dimensional version of the problem. We will then take a break, and then we'll come back, and I will present the two-dimensional version of the problem, strategic scheduling, and auction loss predictions, and then Vasilis will discuss the improved price of anarchy bounds with prediction and conclude as the last quarter. Okay, so that's the plan for the tutorial. So any questions so far? I haven't checked the chats. Okay, so I suppose Vasilis is just monitoring the chat, so I won't look at this too much. Okay, so let's dive into online algorithm. So again, here the main purpose is that I want to kind of like illustrate what has been achieved in this framework of prediction in online algorithm, so that we can then show that we can also have achieved similar benefits for this framework of with predictions for mechanism design. So let me give you some background on online algorithm. Most of you probably already know that. But in online algorithm, we have like different time steps. And at each time step, we have to make some irrevocable decision without knowing the future. Okay, so with only partial information about the instance I that we have at hand. So this is the main information limitation. This is the main challenge. We have to make decisions without knowing what will happen in the future. So the performance measure that is used in online algorithm is the competitive ratio of an algorithm. Formerly, an algorithm is alpha competitive if the performance of an algorithm that is given only this partial information about an instance I is at most an alpha factor away from the optimal value that is achievable for this instance. And here what's important is that for competitive analysis, we always compare ourselves to the optimal value that is achievable if we had full information about the instance at hand. So here, we assume that it knows the entire, it has full information about the instance, it knows the future. Okay. And so for online algorithm, now if we add predictions, what we have is that at each time step we have to make some decisions, but now we have access to some predictions about the future, right? So we have some predictions about the future, but the main difficulty is that in this prediction might be erroneous, right? So we want to do well if the prediction is correct, but we still want there's still this potential for the predictions to be erroneous. Okay. So to illustrate what is achievable here, we're going to consider a very simple and classical problem in online algorithm, and this is the ski rental problem. Okay. So first, I'm going to first discuss what is achievable for the ski rental when we don't have predictions, and we'll see how we can improve on that when we have access to predictions. Okay, so what's the ski rental problem? So in the ski rental problem, every day I'm going to go, every day I go skiing. I'm faced with this decision where I can either rent some skis, and if I rent some skis, I have to pay $1 each day where I go skiing, or what I can also do is just buy some skis. So if I buy some skis, I just pay B dollars once, and then the next days I go skiing, I don't have to pay again. I have my skis that I have bought. And so the goal is to minimize the cost, how much money you spend. And the main difficulty is that every day when you go skiing, you have to make a decision without knowing the number of days that you're going to go skiing. Okay. So first, if we had known the number of days where we're going to go skiing, so in the full information setting where we know everything, what we have done, the optimal algorithm here is very simple. If the number of ski days is at least strictly greater than the price B to buy some skis, what we should do is just buy the skis on day one. And in the other case, we should just rent skis every day, okay? So now what can we achieve in the online setting when the number D of ski days is unknown? What we can do is the following. We can rent the skis for up to B days. And then once we've reached B days of skiing, then at this point, we decide to just buy some skis, okay? So what does this achieve? This algorithm, we guaranteed that you're never going to pay more than 2 times the optimal cost. So in other words, this algorithm is too robust. No matter how many days you're going to end up skiing, you're never going to pay more than 2 times the optimal cost for this number of days that you go skiing, okay? And actually, there's no deterministic algorithm that can achieve a better competitive ratio, okay? So this 2 is the best robustness that you can achieve when D is unknown for deterministic algorithms. Okay, so now what we would want is to it's natural to assume that we maybe have like some partial information about how many days we want to go skiing, and so we would like to kind of like increase. We would like to augment this problem with some prediction. Okay, so here the first thing when we consider a problem with prediction is to ask ourselves, what should be the prediction, right? So this first question of like, what should be the prediction? Here in this context of the ski rental problem, the natural prediction to have, right, is just to have some prediction d hat on the number of ski days. Okay, so we're just going to have some prediction on the number of days we're going to go skiing. And now we have this prediction. As I mentioned earlier, the goal is to simultaneously achieve consistency and robustness, right? And so here, since we're dealing with on an algorithm, we want to achieve a good competitive ratio for both consistency and robustness. So for consistency, again, just as a reminder, now we want to achieve a good competitive ratio when this prediction is correct. So when the predicted number of ski days d hat is equal to the number of ski days d. And we also want to achieve a good robustness when the prediction can be arbitrarily wrong. Okay, so what are some trivial bounds that we can achieve? Similarly as I mentioned before, what we can first do is we can also completely ignore the predictions. So this we can do that if we don't trust the prediction. And then if we run the best online algorithm that we have while ignoring the prediction, which is just to run for up to 2b days and then buy the skis, then we get a 2 robustness and 2 consistency algorithm. On the opposite side, what we can do is that if we completely trust the prediction, we can just run the algorithm with full information, assuming that this prediction is correct. And this would give a 1 consistent algorithm, but it's easy to see that it would also give unbounded robustness if this prediction is completely wrong. Okay, so these are the kind of like the 2 extremes of what we can do. And so now the main questions that arise here is like a first non-trivial interesting bound would be to improve over this worst case bound of 2 when the prediction is correct while maintaining bounded robustness. So, and then more general, what we would really want is really kind of like completely characterize and understand the trade-off between robustness and consistency. Here's what we can do with predictions. So here's what, an algorithm that was suggested. So this is going to depend on the confidence parameter C, which is, you can think about this parameter C as basically how much the algorithm is going to trust the prediction. So if C is equal to 0, it does not trust the prediction. If C is close to 1, it really trusts the prediction. And now what we can do is that if the number of predicted days is larger than the price to buy skis B, so if the prediction here was correct, then we would want to buy some skis on day 1. So in this case, what we can do is that we can just buy some skis earlier than in the case without predictions. So how much earlier should you buy some skis? This is going to depend on how much you trust the prediction. Okay. And now in the opposite case, you can also do the opposite. You can buy some skis later than when you would have bought them if you didn't have predictions. And how much later, again, depends on how much you trust the prediction. So this simple algorithm achieves a consistency of 1 plus C and a robustness of 1 plus 1 over C. So now there's 2 nice ways to kind of like visualize this result. So the first is to kind of like, we can look at the consistency and the robustness as a function of C. So you can think about C as kind of like a knob that the algorithm control, and that kind of like trade-offs this consistency and robustness. And so here we can see this trade-off. And another way to see this is that it gives kind of like a Pareto frontier on the trade-off between consistency and robustness that's achievable. Okay. So now the natural question, once you have this consistency and robustness, is can you actually do better? And it was actually shown that that this is the optimal trade-off that is achievable for any values of C. So for any values of C, any 1 plus C consistent algorithm is going to be at least 1 plus 1 over C robust. Okay, so next, as I mentioned before, we would like to extend this consistency and robustness result to also hold as a function of the prediction error, right? So if the prediction is not exactly correct, but almost correct, we would still want to get some improved competitive ratio. So now here, the main question we should ask ourselves is, how do we define the prediction error? So here, a natural way to define the prediction error is how far, so just the absolute distance, the absolute difference between the predicted number of ski days and the actual number of ski days, which we're going to denote eta. And now we would want to have a competitive ratio that's as a function of eta that's smoothly interpolated between the consistency and robustness. And we can see, and there's a result that shows that this algorithm with prediction that I just presented actually achieves a quantitative ratio of, that is the minimum of 1 plus 1 over C and 1 plus C plus eta over 1 minus C over times opt. So here, this 1 plus 1 over C is the consistency, it's the robustness. So you can see that you have this 1 plus C, which is the consistency. And then as a function of eta, it's going to grow, but it will never go over the robustness bound of 1 plus 1 over C. Okay, so this was kind of like some background on this. This kind of like concludes the part of the tutorial that shows you what is achievable with this framework in the context of online algorithm. And hopefully this sets the stage for Vasilis, who will now discuss about how to use this framework for mechanism design. So while we switch, I will stop sharing my screen, but now is a good time to ask questions in the chat.
Yeah, and if you have any questions regarding any slide, I can roll back to the corresponding slide. So we'll take a couple of minutes to make sure people ask questions, that you understand the definitions, and you have any kind of questions about the online algorithms aspect of the presentation. Either in the chat or you can use the microphone. And by the way, while we're waiting, in case anyone has a question, let me point out that we really plan, since there's not that much new kind of work in this direction, mechanism design with predictions, this is brand new. We plan to kind of go slowly over some examples of the known results and kind of try to provide intuition about how to come up with solutions and how to achieve both robustness and consistency in the trade-offs. So we will pause in between, have you think about what to do before we provide the solution. So we plan to make it interactive. So, hopefully you're in the mood to think about things more than being kind of passive, presentation mode. Okay, so yeah, and from now on, kind of Eric will be monitoring the chat. So let me start with the second quarter of the tutorial. And as the slides here show, we're going to focus on this paper that actually will appear at EC this year, 22, on strategic facility location with predictions. This is where we essentially introduce this model of mechanism design with predictions and focus on this particular problem of strategic facility location, a canonical problem. And I see there's a question.
Yeah, I can take care of
Go ahead. You can answer, I guess, also to everyone. We can consider that part of the break.
Okay. Sure. Yeah, so there was this question about is C related to some prior we have? Is C high if it's close to our prior? Yeah, good. So C is really, it's the algorithm designer that gets to pick it. And this, so if the algorithm has some prior on how much it should trust the prediction, then they can use that to inform how the algorithm should pick C. But as the bounds show, there's basically this trade-off between consistency and robustness, and this trade-off is controlled by this parameter C. But in general, we don't assume that there is a prior about it. It's just the algorithm designer who gets to pick it.
Yeah, or alternative, you can think of it as a family of algorithms. You can choose whichever you like. Depending on the C, you get to choose a different algorithm. So you don't need to know, essentially, if you want really a good consistency bound, you can, choose the C so that it focuses on consistency, and that provides a trade-off. And we'll focus on that also later on, and kind of another mechanism on facility location, on, essentially giving the whoever runs the mechanism or the algorithm the chance to determine, which trade-off are they going for? How much do they care about robustness, or how much do they care about consistency? And that is the kind of great thing about this framework. It provides you with this choice whenever you can design algorithms with that. And I should say this is joint work with Eric. This paper, we're going to be spending a lot of time discussing, trying to focus on just one setting and expanding, trying to provide intuition of how we can use predictions in mechanism design rather than just algorithm design. And it's joint work with Eric Balkanski and also Priyank Agarwal and Ting Wu, who are students, PhD students at Columbia, and Sijie Tan, who's a PhD student at Drexel University. And this is also part of a broader agenda that Eric and I have. It's kind of recently funded NSF project we submitted last year on mechanisms with predictions, or learning-augmented mechanisms. And the difference here is that, unlike online algorithms, for instance, where the main information limitation that the prediction helps you with is that we don't know part of the instance. Just like in ski rental, we did not know exactly how many days we're going to be invited for skiing. In mechanism design, there's going to be some different information limitation. And of course, it's obvious to people who have worked on mechanism design that, of course, the natural thing that arises is that we don't know the private information. The main obstacle in mechanism design compared to algorithm design is that part of the information is private and held by the agents. And therefore, that's what makes it harder. And that's where the predictions can be particularly helpful. So, and the fact that the agents are strategic means that they can misreport this information. The mechanism might need this information in order to come up with an efficient or appropriate solution. But the agents might strategically misreport it if that benefits whatever their goals are. And just like in algorithm design, where we use worst case analysis, similarly in mechanism design, whenever worst case analysis is used, it often leads to pessimistic lower bounds impossibility results, meaning we conclude that we cannot get a good approximation, we cannot get a positive result in the worst case if we want to maintain strategy proofness, meaning we want to make sure that people are never going to lie about this information that we're trying to elicit. And we're going to be, the big part of this kind of tutorial is going to focus on centralized mechanism design with predictions, which is, you can think of it as just the standard mechanism design with setting, where some information is private and the participating agents hold this information. We want the mechanisms to be strategy proof. In other words, that we want them to be truthful. We want to be a dominant strategy for the participants to tell the truth about this information. And we have predictions regarding this private information. And the question is, can we use this to get more practical solutions where somehow we use this information to get better outcomes? But the last part of the tutorial is also going to focus on decentralized mechanisms with predictions. So this is not the classic mechanism design setting. This is more like the price of anarchy problems, the classic price of anarchy problems that have been studied in the community in algorithmic game theory, and try and understand how decentralized protocols or mechanisms can lead to better outcomes. And then the information limitations are going to be, the source is going to be different. It's going to be decentralization, but we'll come back to this toward the end of the tutorial. So for now, let me come back to learning-augmented mechanisms. And the input, just like in algorithms with predictions that Eric presented, is going to be some prediction. And the crucial part for everyone to understand here is that this prediction can be arbitrarily inaccurate. It could be accurate, it could be providing us good information, but we're not assuming that. It could be arbitrarily bad. And the performance evaluation is not just based on one metric, it's based on two separate metrics. We provide a consistency guarantee, which means if that prediction happens to be accurate, we want to restrict the mechanism to achieve good bounds, better bounds, whenever this is accurate, but without compromising, without just totally throwing away robustness, meaning we still want to maintain the benefits of worst case guarantees. So even if the prediction is horrible, somehow it's totally misguided, we still want to make sure we get some kind of robustness guarantees. And there's other settings that have been studied recently in algorithm design, for instance, the advice setting, just to make sure we separate those out. So in this setting, the input is actually still a hint, kind of suggesting something about the input, about the instance. But in that case, we know how much we can trust this. This comes also with a probability that tells us how likely is it that the advice is accurate. And then in that line of work, the performance is evaluated in expectation based on that probability. So we know in advance how much we should trust the prediction, the advice we provided, whereas in learning augmented mechanisms and algorithms, there's no such guarantee. We have no sense of how much we should trust the prediction. We just want to get worst case guarantees, both for consistency and robustness. And finally, before I go into this facility location problem, strategic facility location, I think it's important, especially for people that have worked in mechanism design and might be thinking, oh, there's some, of course, related line of work on the Bayesian setting, where we assume that we have some distributional information regarding the participating bidders. And of course, classic mechanism design results use this information to get better bounds. Again, I want to emphasize the important distinction here is in that literature, the assumption is that the priors are accurate. We know that they are correct. And in fact, the performance of the mechanisms is evaluated in expectation based on that prior. So we're assuming the prior is correct and that the evaluation is, again, there's no robustness guarantees. If this prior is horrible, is somehow totally misguided, there's no guarantees that we are provided by this line of work. So again, this is the important distinction and important novelty, that we don't throw away robustness. The benefits of worst case analysis are we try to maintain those while also benefiting from informed predictions. Finally, one kind of side point is also that some of the work on the Bayesian setting relaxes the notion of strategy proofness to Bayesian incentive compatibility. Again, we're not going to be doing this here. We're going to be focusing on strategy proofness as a hard constraint. And as we mentioned before, and questions at any point are more than welcome. In fact, I will be pausing quite a bit during this strategic facility location part, so you can ask questions or even think about what you would do to design a mechanism for the problem. So the strategic facility location problem goes as follows. So we're going to be focusing on R squared, so the two-dimensional Euclidean square. So each agent is going to have a preferred location Pi in R squared, in the two-dimensional Euclidean space. And we need to choose a facility. We're going to be focusing on a single facility location problem in this space. And the cost of each agent, once we choose a facility, is going to be the distance of their preferred point to the facility point that we output. Right? So in this case, for instance, the agent whose preferred point is this black point on the top right, if we choose the yellow star as the facility location, that distance, the Euclidean distance, is going to determine how unhappy they are with the final choice. And our goal is going to be to choose how to place a facility in order to minimize some social cost. It can either be the egalitarian social cost, in which case we're trying to minimize the maximum over all agents, or the utilitarian social cost, where we're trying to minimize the average cost over all agents. These are the two classic objectives, and we're going to be studying both. And this is also interesting. This has been studied from an algorithmic perspective purely, if we have full information, but it's also has been a canonical problem when in the strategic version of it, where the preferred location of the agents are private, meaning we do not actually know where these black points are. We expect the agents to report them to us, and they would lie if that actually moves the facility closer to where their true point is. And that's what makes the problem harder, is that we don't actually know the input. We need to design the mechanism, making sure that people are not going to lie. And just to get a better sense of this problem, let's just think about the one-dimensional case. So that's what I'm going to be focusing on this first part of the tutorial, and Eric will then extend this to the two-dimensional case. So in the one-dimensional case, these points are all on a line. So each point here that you see on this blue line is the preferred location of each one of the agents. And in the utilitarian social cost, remember, we're trying to minimize the average. We're trying to choose a facility that minimizes the average. And in fact, if you think about it, the optimal choice in that case would be to output the median point. If you think about it, if we choose, if we move this facility further to the left, we're hurting 6 people. You see there's 6 points on the right. If we move it by an epsilon, we're hurting people on the right by epsilon, 6 people, and we're benefiting only 5. If we move it to the left, same thing. So we don't want to move the facility anywhere else. The median point would be the optimal solution. And in fact, conveniently for the utilitarian social cost, choosing the median point is actually a strategy-proof mechanism, meaning if we tell the participants what we're going to do is we're going to take the bids, see everyone's reported location, the point where they most prefer the location to be, the facility to be, then order them and take the median. If we just say so, they will not have any reason to lie. Again, this is reasonably easy to verify. And anyone who, so if the person who actually has the median point were to lie, of course, clearly they're just moving the facility away from the point that they actually prefer. If anyone else lies, they can only change the location if they become the median. If they move, if they become the median and kind of change the actual location, but they can only move it away from their preferred point. And I don't want to spend too much time here, but the main point here is that for the one-dimensional case and the utilitarian social cost, actually we can get the optimal solution even in the strategic setting. We can just output the median and get the optimal solution, and nobody ever has the reason to lie about their points. However, as we're going to see in the second half of the tutorial, this is not true anymore for 2 dimensions. But for the egalitarian social cost, the problem is actually interesting even in the one-dimensional case. So let's remember, egalitarian social cost means we're trying to minimize the maximum. We're trying to make sure that the person who is least happy, we're trying to make him as happy as possible, right? We're trying to minimize the maximum cost over all agents. So algorithmically, if you think about it, the best thing to do is to actually look at the leftmost point, the rightmost point, and place the facility right down the middle between these 2 points. Any other facility location, for instance, if the facility was further to the left, that would hurt the rightmost point more. The maximum cost would be higher. Again, if we move the facility to the right, the leftmost point would be have a higher cost. So the best thing to do is to go right down the middle. However, this time around, if you think about it, if we were to just say, you know what, I'll just, again, do the same thing. I'll output the optimal point. I'll ask people to report their points, and I'll output the optimal facility location right down the middle. It's not hard to verify that then people will not be truthful. For instance, the rightmost agent will have reason to just say he's even further to the right so that he actually brings the facility is closer and closer to their real location. So they can pretend that their point is further away, excuse me. Instead, one thing we could do is output the median again, which is not going to be the optimal solution, but it gives us a 2 approximation no matter what. So it always guarantees a 2 approximation of the optimal social cost. And as we saw before, it is actually strategy proof. So that gives us 2 robustness. And in fact, we know that this is as good as we can hope to do with any deterministic strategy-proof mechanism. So if we want the strategy-proofness with the deterministic mechanism, 2 approximation is all we can hope to achieve for the egalitarian social cost in a single-dimensional setting. Okay, so the question is, this is one of those bounds where it somehow feels maybe it's unnecessarily pessimistic. So the question that we ask, and this is the point where predictions are becoming relevant, is what can we actually do? Can we actually do better if we had some prediction? Can we get better than a 2 approximation if the prediction is accurate? So I want you to pause for a minute and think here. What would be a reasonable choice for a prediction in this setting? What would be the appropriate prediction? What would be provided as a prediction that would be useful for the mechanism? And as I mentioned before, the private information is what we're really missing, right? Otherwise, it would be just a purely algorithmic problem, and in fact, a simple one. So what would be useful is to actually have the actual player's location as a prediction. If we knew for every player what their preferred location would be, that would make our life much easier. So if we had a prediction over that, that would actually be really useful, right? And if we had that information, maybe we could use it to improve the performance of the mechanism. However, instead, what we do in this work is we make an even weaker assumption. Rather than assuming we need to know all this information, we instead assume that the prediction just tells us where the optimal facility would be. It's a prediction, a single point prediction rather than endpoints, one for each agent, that tells us here's where I think the optimal facility should be placed, right? And it's easy to verify that, of course, if you knew the first prediction, if you had a prediction over all the agent's points, you can quickly compute the second, right? So it's strictly less information. So it's easier to predict in that sense. So it's a single point as a prediction. But again, the question is, what if we had this information? Can we achieve better consistency? And what's the robustness? So again, consistency is the approximation achieved if that prediction we're provided with is accurate. And robustness is the approximation achieved when the prediction can be arbitrarily wrong. Okay? So one extreme would be to see, I want one consistency, right? I want to guarantee that I will get one consistency, meaning if my prediction is correct, I want to make sure I get the one approximation. I actually output the optimal solution. So an easy way to do that would be to just return the prediction. Always say whatever the prediction says, when the prediction says, here's what the optimal facility location would be, just go with that. And that would give us a one consistency. However, it would give us unbounded robustness, because if the prediction is horrible, if somehow it's really off, our worst case guarantee would not provide any type of bound, right? So this is not an ideal way to go. An alternative solution would be to go with a median mechanism, just as we saw before. And that would give us true robustness. That would make sure we have bounded robustness, but it would not give us better consistency, because essentially we're disregarding the prediction, just like Eric pointed out before. Right? So these are always two obvious options. We can get one consistency with no robustness. We can get robustness and the same consistency. But the interesting question, where all these mechanism design with predictions become interesting, is can we actually get any better consistency? Can get strictly better than two consistency, but still get some robustness? Do not not getting unbounded robustness. And in fact, in general, is there a trade-off? Does better consistency need to come at the cost of robustness? Okay. And let me just here let you think about for a minute, what would you do? So you want a mechanism that, like given these points, your input is going to be these points of what people reported as their locations. And you also get this red point, which is the prediction, what the prediction tells us the optimal facility location would be. What would you do? How would you use this information, this red point? How would you use it without breaking strategy proofness, without violating strategy proofness, getting good consistency, but not losing robustness altogether? And that's the interesting problem. And again, we're exhibiting this in the facility location problem because it's nice and clean way to exhibit the results, but this will apply in general for mechanism design. How do you use this information to guide your choices, but not losing robustness altogether, not trusting it too much, and not sacrificing strategy proofness? And I'm pausing for a minute to make sure people think about this. What would you do if you're given this? And let me just go. So I see that Clay suggesting maybe breaking but let me just go for a few more seconds just to wrap up, show this mechanism first. Then, next slide, we can wrap up. So the mechanism that we propose is the following. If the prediction is between the minimum and the maximum points, you can just return the prediction. So in other words, if the prediction, just like in this case, is between the minimum and the maximum point, we output the prediction itself. If, on the other hand, the prediction is not between the minimum and the maximum, then we return the point that is closest to the prediction. For instance, if the prediction was somehow far off to the left, then we would output the leftmost point. Okay? And as it turns out, this mechanism is strategy proof. It doesn't violate strategy proofness. It is one consistent. Whenever the prediction is correct, it will always get the right outcome, and it is too robust. So it is important to emphasize this is getting the best of both worlds. This is not sacrificing robustness at all and is getting the optimal consistency. So if our prediction was accurate, we get the best solution, but we still maintain the best possible worst case guarantee. And to verify this, the idea is that if the prediction is accurate, it will be somewhere between the leftmost and the rightmost point. And if it is outside, it is going to be essentially nobody will want to misreport the locations. Essentially, if we choose the leftmost agent in this case, if the prediction is all the way to the left from everyone else's preferred location, and we choose the leftmost bidder, then nobody will want to lie. The only way in which they can change the outcome is moving it further to the left. In fact, we don't just get a result for consistency and robustness. We also get a result that's parameterized by the error of the prediction. So in particular, what if the prediction is not exactly correct? Do we just lose everything? We get one consistency if it is exactly correct, but what if it's almost correct? So if we define eta as the prediction error, which is the distance between the true optimal solution and the predicted optimal, optimal location, the predicted optimal location normalized by opt, then the bound that we get is actually that the mechanism above achieves an approximation of which is the minimum of 1 plus eta plus comma 2. So as long as eta, the error, is no more than 1, we actually get an even better bound. So even if the error is significant, but less than 1, the normalized error is less than 1, then we still get a better bound. So this smoothly transitions from eta being 0, which is the perfect prediction, and eta being really high, where, as Eric showed before for ski rental problem, we never go beyond 2. And let me finish up with this slide as a puzzle for the break. You have half hour. Maybe some people might want to think about it before Eric presents this. What about the two-dimensional case? Can some of this intuition extend to the two-dimensional case? Again, in the two-dimensional case, we can achieve a two approximation in robustness. Any point in the convex hull, if we take the convex hull of these points, any point in the convex hull would give you a two approximation. But what if you want better than two consistency? What would you do? How would you achieve this? Better consistency without sacrificing robustness, or maybe not sacrificing it too much. So I think this is a good thing to maybe think about during the break, so that then when Eric explains a solution, what we can do in this setting, it will make more sense. So now I think, as Clay suggested, is a good time to take a break. We'll be here to answer any questions that you might have.